The Recovery Couch is made possible by the generous support of our sponsors. A special thank you to Greg Swartz at Remax Victory and Affiliates. Greg is more than just a real estate expert. He's a leader in our community who believes in helping people find their way home, both in life and in faith. If you're looking to buy or sell, connect with Greg and experience the integrity and service that he gives. We're also proudly sponsored by JB Davis at South Dayton Toyota, where community commitment and care come standard. JB and his team don't just sell cars, they support local voices that help inspire change. Together, these partners make it possible for us to keep sharing stories of redemption, resiliency, and recovery. The Recovery Couch is a true story media production, reminding you that every story matters and healing begins when we speak out loud. Hey, what's up, guys? Welcome back to the Recovery Couch. I'm your host, Brandon Couch, and today we're diving back into episode 3 of our series, Learning Together, where we're taking a deep dive into everything there is to know about addiction and recovery. Today, we're diving into the neurobiology of addiction. So we're going to discuss how do psychoactive drugs affect our brain, our nervous system, and the specific neurons, axons, and the electrical impulses, and how our bodies adapt to these psychoactive drugs. So in order to understand that, we need to understand the human anatomy, which takes us eventually into the neurobiology, which is what's going on in the head. How are these psychoactive drugs affecting our brain? So in understanding the effects of psychoactive drugs, it's important to understand the nature and the function of the nervous system. The nervous system is comprised of the specialized structures that control and coordinate all body activities. This is through the process of stimulus and response. So what stimulates us, and then how do we respond to it? That's going to be our nervous system. The process of stimulus and response occurs in 3 stages. The first stage is sensory reception. Some type of stimuli is detected either from outside or within the body. You hear a loud noise. A car alarm goes off. You hear somebody slam the hood of their car. This would be a sensory reception. You hear the stimuli, and it's detected from either outside or within the body. Maybe you jolt because you get a really bad itch on your elbow. Stimuli is detected. Sensory reception. The second stage is interconnection, where the stimuli creates an electrical message that is then transmitted from one part of the system to another. So this would look like, interconnection would look like the car alarm goes off and it was so close to you in proximity that you react and jump. The response to the stimuli was transmitted from the sound to your brain. That's interconnection. You respond to the stimuli. The third stage would be motor response. So an appropriate response is triggered, such as a muscular contraction as a result of message being sent back to the body part by a nerve center. So the car alarm goes off, you jolt, and then all of a sudden you get a response back to your head and you get a headache. That would be a motor response. It's not a great example, but it is an example nonetheless. The nervous system consists of 3 major structures. So our nervous system, every human body's nervous system, and this is why the science of addiction is important to know, because these psychoactive drugs have the same effect on anyone who takes them, just based off of anatomy and physiology and biology alone. So sometimes I've heard people say, like, that drug don't affect me that way. Well, yes, it does, because you're built up of the same components as every other human being in the world. So the nervous system consists of 3 major structures: the brain, the spinal cord, and the peripheral nerves. The nervous system has 2 major parts. The central nervous system, okay, so that's going to be composed of the brain and the spinal cord. That's your central nervous system, right? So we just said the nervous system contains three major structures: brain, spinal cord, and peripheral nervous system. The central nervous system only includes the brain and the spinal cord. The peripheral nervous system is the second major part of the nervous system, and it consists of all the nerves that branch out from the central nervous system and connect the system to other body parts, including the hands and the feet. So imagine in your head seeing, one of those images that they provide us in science class back in, high school. And you're learning the human body. In one image, they show you the skeletal structure of the human body. In another image, they show you the muscular structure of the human body. And then another image, they show you the nervous system. And the one that I remember seeing in high school had nerves, it had the brain, it had the spinal cord, and then it had like red and blue lines coming out of the spinal cord. Those red and blue lines coming out of the spinal cord, that's the peripheral nervous system. So basically, those are the nerves that are sending the stimuli to, different parts of your body. Additionally, there are two subdivisions of the peripheral nervous system. There's the somatic system, okay, and the autonomic system. The somatic system is comprised of the cranial and spinal nerves, which connect the central nervous system to the skin and to skeletal muscles. Okay, so just like there's two major parts of the nervous system, the central nervous system and the peripheral nervous system, there's also two subdivisions of the peripheral nervous system. Okay, so the somatic system is the first subdivision of the peripheral nervous system, and it is comprised of the cranial and spinal nerves that connect the central nervous system to the skin and skeletal muscles. Okay. The second subdivision is the autonomic system, and that's the nerves which connect the central nervous system to various body organs. This includes the heart, the stomach, the intestines, and various glands. These nerves function involuntarily. They're controlled by the brain automatically, which without control, without effort, the autonomic system is controlled by the brain, and the nerve functions involuntarily. So the somatic system, we can function those nerves voluntarily. The autonomic, those nerves function involuntarily. Of the autonomic system, there are two subdivisions as well. The sympathetic division, which prepares the body for activities which expand energy, running, jumping, hiking, walking, and the parasympathetic division, which aids the body in returning to normal after a period of expending energy. So the parasympathetic aids the body in returning to normal after a period of expending energy. The parasympathetic division works to counterbalance the activities of the sympathetic division. Okay, so that's a lot. So this is a very scientific episode, but I'm trying to take as many breaks as I can to create parallels, illustrations, imaging, pictures to help us understand as possible. The neuron is the basic unit of the nervous system. We've all heard of neurons. It's capable of both receiving stimuli and transmitting electrical messages or impulses throughout the system. Extending from the neuron are two types of nerve fibers. So the neuron is the basic unit of the nervous system, capable of receiving stimuli and transmitting electrical messages. So if we hear stimuli, if we smell stimuli, if we see stimuli, the neuron fires and it receives the stimuli. But if there's an internal stimuli, it can also transmit electrical messages throughout our entire nervous system. Extending from the neuron, that's a tough word, dude, are two types of nerve fibers. There's dendrites, and those are fibers that send nerve impulses toward the cell body. And there's axons. Axons carry impulses away from the cell body. Each neuron has several dendrites, but only one axon. So for every neuron, they can have a myriad, a multitude, a lot of dendrites, which are the fibers that send nerve impulses toward the cell body. But every neuron only carries one axon. And the axon is what carries impulses away from the cell body. Electrical impulses originate in the dendrite and are then transmitted down the axon. Psychoactive drugs do not act primarily on the axon, with the exception of local anesthetics. And that's because local anesthetics blocks the transmission of pain impulses to the brain completely. I did not know that. At the junction between the axon of one cell and the dendrite of another, known as the synapse, the electrical impulse must cross a narrow space or gap called the synaptic cleft, CLEFT. This gap is filled with a special type of fat that acts as an insulator between the cells. The crossover process is accomplished not by electrical impulse, but by chemical transmission. It is here that other chemicals, specifically the psychoactive drugs, have their major effect. Okay, so let's break that down. There's a lot there. So at the junction between the axon of one cell and the dendrite of another, known as the synapse. So the axon carries the impulses away from the cell. Then it meets with the dendrite that send nerve impulses toward the cell body. At the junction between the axon of one cell and the dendrite of another, this is called the synapse. So at that synapse, the axon meets the dendrite, the synapse, the electrical impulse must cross a narrow space or gap called the synaptic cleft. This gap is filled with a special type of fat that acts as an insulator between the cells. The crossover process is accomplished not by electrical impulse, but by chemical transmission. So at the synaptic cleft, sounds like that is going to be where the drugs cross from between. We're going to find out. Let's find out. It is here that other chemicals, specifically the psychoactive drugs, have their major effect. Depressant drugs tend to thicken the medium, thus slowing down the transmission, while stimulant drugs tend to thin the medium, thus causing a more rapid transmission. Certain types of drugs, especially marijuana, have been found to actually fill the gap, thus preventing the transmission from occurring. Let's go back. The transmission again is the synaptic cleft. The axon is meeting the dendrites. The electrical impulse must cross a narrow space or gap called a synaptic cleft, and this gap is filled with a special type of fat that acts as an insulator between cells. That's if there's no drugs in the body. This is what's happening to just the stimuli. But then if you put a drug in the body, a psychoactive drug, let's use marijuana for example, because it gave a good example in the book, then at this synaptic cleft, the marijuana has been found to fill that gap, not allowing that crossover to take place, the chemical transmission. So it stops electrical impulses. It stops the human body's ability to receive and transmit stimuli. Depressant drugs tend to thicken that medium at the synaptic cleft, which slow down the body's ability to receive stimuli. Stimulant drugs thin the medium, thus causing more rapid transmission, which means more stimuli. You're stimulated. This is scientifically, anatomically, biologically what goes on in the human body. Why does cocaine affect? Why do I feel so stimulated when I take cocaine or methamphetamine, any sort of stimulant, Ritalin? Why do I feel so stimulated? It's because the stimulant thins the medium at the synaptic cleft, allowing for more stimuli to pass through. The depressants thicken at the synaptic cleft. In some cases, marijuana completely closes it, which slows down the stimuli, your body's ability to feel stimulated to surroundings, period. Any sort of surroundings, period. Which is why people will describe depressants, marijuana as chill or laid back. They have anatomically, biologically, their body is unable to be as stimulated as somebody who is not on drugs or somebody who is on stimulant drugs. When an electrical impulse reaches the end of an axon, tiny sac-like structures known as synaptic knobs manufacture chemicals called neurotransmitters. Like we've all heard of neurotransmitters. So the axon, let's not forget what the axon is. They carry impulses away from cell bodies. So when there's an electrical impulse reaching the end of an axon, tiny sac-like structures known as synaptic knobs manufacture chemicals called neurotransmitters. Then the following sequence of events occurs, and then it occurs rapidly. A nerve impulse reaches the synaptic knob. A neurotransmitter substance is released into the synaptic cleft. Remember, that's the area that either thins or thickens, the synaptic cleft. The neurotransmitter substance is diffused across the synaptic cleft. So this substance that was created it's getting diffused across the synaptic cleft. The neurotransmitter reacts with the membranes of the dendrite on the other side of the cleft. The dendrite is the fiber that sends nerve impulses towards cell body. So if, in this case, the neurotransmitter reacts with the membranes of the dendrite, if the neurotransmitter is a depressant, then it's going to start sending nerve impulses, depressant type nerve impulses, to the other side of the cleft. If it's a stimulant, it's going to start sending stimulant to the other side of the cleft. And then the nerve impulse is reestablished in the dendrite and transmission is continued through the cell. Now the stimulant or the depressant is reaching our cells, and the neurotransmitter substance breaks down to prevent continued stimulation of the dendrite. The book shows a pretty detailed image of what it looks like. All right, there are a variety of neurotransmitter substances within the nervous system. Among these are acetylcholine, which is an excitatory neurotransmitter released by axons. Norepinephrine. Whew. That's a neurotransmitter found in the brain associated with arousal, reactions, and moods. Dopamine. Dopamine is a neurotransmitter found in the brain associated with body movement and pleasure. Serotonin. Serotonin is a brain neurotransmitter associated with regulation of sensory perception, sleep and body temperature. Alterations in the serotonin functioning have been found to be related to mental illness and certain drug-induced hallucinations. Gamma-aminobutyric acid, or GABA, is an inhibitory neurotransmitter substance, one that blocks the transfer of a nerve impulse to an adjoining neuron in the brain. When the normal function of GABA is disrupted, convulsions may occur. So, for instance, when I was coming off of benzodiazepines and I had involuntary tremors and eventually seizures, that was because my normal function of GABA was disrupted, which caused convulsions and seizures. Glycine is an inhibitory neurotransmitter substance found in the spinal cord. Enkephalins and endorphins were first discovered in 1975, are both compounds that have been extracted from the brain and pituitary gland, and both of these compounds have pain-killing properties that are more powerful than morphine. That's interesting. With endorphins being 40 times more powerful than enkephalins and 100 times more powerful than morphine. That's crazy. Endorphins are strong. They're strong things. So when you hear someone say releasing endorphins, those endorphins are 40 times more powerful than their counterpart, enkephalins, and the endorphins are 100 times more powerful than morphine. That's an interesting fact. All right, so the life cycle and action of neurotransmitters. So it appears that the neurotransmitters that are used to communicate between neurons are made inside the brain cell from which they are to be released. A cell that is going to make a particular neurotransmitter may need to bring in the necessary precursor in a greater concentration that exists in the whole brain. Brain cells apparently have a mechanism built into that cell's membrane for active uptake of the precursor. After the precursor molecule has been taken up to the neuron, it must be changed through a series of chemical reactions into the neurotransmitter molecule. This process is known as synthesis. At each step of the synthetic chemical reaction, the reaction is helped along by an enzyme. These enzymes are themselves large molecules that recognize the precursor molecule, attach to it briefly, and hold it in such a way as to allow the synthetic chemical reaction to occur. When the neurotransmitter molecules have been synthesized, they are stored in small round packages in the synaptic knob, which is found at the end of the axon. We've talked about that. These are called synaptic vessels, from which they will be released. When an electrical signal arrives from the neuron to the synaptic knob, some of the vesicles fuse with the cell membrane and then open, releasing many thousand neurotransmitter molecules at once. This process of neurotransmitter release takes place within a few thousandths of a second after the electrical signal reaches the synaptic knob. So this is all in the process of neurotransmission. Once the neurotransmitter molecules are released into the small synaptic cleft between neurons, a particular molecule may just be floating around, or it may be one of the ones that bind to the receptor on the dendrite of the next neuron. This receptor represents the most important recognition site in the entire process, and it is also one of the most important places for drugs to interact with the natural transmitter. That's because there's literally thousands of neurotransmitter molecules floating freely in the synaptic cleft. Some will come near these receptors, bind to them briefly, and then float away again. In the process of binding, the neurotransmitter may distort the receptor so that a tiny passage is opened through the membrane, allowing an electrical current in the form of charged ions moving through the membrane. This opening does not last long, however. Within a few thousandths of a second of the neurotransmitter molecule has left the receptor, the ion channel is closed. The small localized electrical current found at a single receptor might not have much effect all by itself. However, these electrical currents do spread, and if enough receptors are activated at about the same time, then an electrical signal will be sent up to the dendrite to the cell body of the neuron, then all the way down the axon to the synaptic knob, and the transmitter will be released there. It is this action which takes place over and over that creates the electrical signals which carry information in and around the brain. Because activity in the nervous system occurs continuously and at a high rate, once a signal has been sent from one neuron to another, it is important to terminate that signal so that a new signal can be transmitted. Therefore, the thousands of neurotransmitter molecules released by a single electrical signal must be removed from the synaptic cleft. Two methods are used for this. In some cells, a process of reuptake takes place, in which the neurotransmitter is recognized by a part of the membrane on the neuron from which it was released, and the other is with other neurotransmitters. Enzymes present in the synapse metabolize or break down the molecules. This appears to be especially true with the neurotransmitter dopamine. So now to the stuff you've all been waiting for, examples of drug actions. So the reason for learning about the action and the life cycle of a typical neurotransmitter molecule is so that we can understand how foreign molecules that enter the brain in the form of psychoactive drugs tend to interact with and alter the normal mechanism for synthesizing, storing, releasing, binding, reuptaking, and metabolizing the same neurotransmitters that we just talked about. One drug that interferes with the synthesis of the neurotransmitters dopamine and norepinephrine is methyl-dopa, which is used to treat high blood pressure. Methyl-dopa, spelled METHYLDOPA, looks like DOPA, one of the chemicals produced during the synthesis of dopamine and norepinephrine. In the autonomic nervous system, methyl-dopa is acted on by some of the enzyme molecules that normally act on dopa. The eventual result is the creation of false norepinephrine, which is methyl norepinephrine, which the neuron then stores and releases along with some regular norepinephrine molecules. However, the false norepinephrine molecules do not activate the norepinephrine receptors in the heart or the blood vessels. Since norepinephrine usually causes increase in blood pressure, the false norepinephrine molecules reduce this effect. The majority of drugs have their actions and effects at the receptor sites of neurotransmitters. Because the drug molecule resembles the natural transmitter in its structure, the receptor recognizes the drug molecule. then the drug molecule may have the same type of action as the neurotransmitter itself does on those receptors. For example, the stimulant drug amphetamine is structurally similar to norepinephrine and dopamine. And one of its effects is to mimic norepinephrine at its receptors. So amphetamine has a similar chemical compound as norepinephrine and dopamine. So the neurotransmitter is tricked into believing that the amphetamine is either norepinephrine or dopamine, and it binds at the receptors. In other cases, a certain drug molecule may bind to the receptor but not activate it. For instance, not distort it so as to open an ion channel. If there are enough drug molecules and they have enough of a tendency to bind to the receptor, they may prevent most of the neurotransmitter molecules from having access to a receptor. The major tranquilizers such as chlorpromazine or thorazine, which are used in treating psychotic behavior, act by blocking receptors for dopamine in the brain. So thorazine will block the receptors for dopamine. So you cannot receive dopamine, thus reducing the activity in those dopamine pathways. Science. Some drugs work by slowly removing a neurotransmitter from the synaptic cleft so that the molecules stay around and continue to bind to the receptors for a longer period than normal. The stimulant drug cocaine interferes with the reuptake of dopamine and norepinephrine, thus effectively increasing the duration and magnitude of each signal in those pathways. However, if too much neurotransmitter is left in the synapse so that the receptors are constantly bound to the neurotransmitter molecules, information flow can cease completely. One of the most dramatic examples of this effect are the nerve gases, which are made up of molecules that bind irreversibly to the enzyme that normally breaks down the molecules of the neurotransmitter acetylcholine. With the enzymes thus tied up, the acetylcholine rapidly builds up in the synapse, and within minutes of exposure to a lethal dose of nerve gas, respiration ceases and suffocation results. All right, that's a lot for today. We're going to end it there. The next episode, we're going to talk about the brain. Okay, so that's a lot to process. You might have to watch some of this, look back and listen to some of it, maybe even pull out some diagrams or use Google to help you gain an understanding. That is certainly a lot of information. So we're going to keep this episode short. Remember to go check out my book, Step 4, Journey Through Addiction. It's available now wherever you buy your books, book retailers. I have them for sale. If you want to, I'll leave a link in my bio. And yeah, go check out the book. Also check us out, the Recovery Couch Inner Circle on Patreon. We got a Patreon page. Check us out there. And remember, you always have a seat right here on the Recovery Couch.